Hello, and welcome to this presentation on matrices. This is an introduction to matrices, looking at basic terminology and arithmetic operations such as addition, subtraction, and multiplication of matrices. Here's an illustration of a matrix where quantities of fasteners from various shop floor assembly sequences are shown. Assembly A, B, and C. We have nuts and bolts, blind rivets, solid rivets, and screws. In each of the columns here we have the number, in this case, of nuts and bolts. In each assembly we have the number of blind rivets in each assembly, number of solid rivets in each assembly, and number of screws in each assembly. These quantities can be written as an array contained in a curved bracket form, and this is known as matrix notation. So here are curved brackets around the above information, which forms a matrix. Matrix algebra. You will see in this presentation that we can add matrices together, we can subtract matrices, we can multiply matrices, but we cannot actually divide matrices. That's not possible in matrix notation. We have to find what's termed the inverse of a matrix, and we review that in a later presentation. Application of matrices. Matrix methods are used in engineering and in science, mainly for solving linear simultaneous equations. Matrices can also be used for the purposes of translating, mirroring, rotating, reducing, enlarging various objects. And such operations are often performed by computer-aided design, CAD graphical packages. Matrices are also used within both static and dynamic stiffness analyses for assessing structural deflections and vibration modes. Here is shown a typical stiffness matrix for an element shown on the left-hand side of a matrix model. Each of the columns in the matrix relates to a degree of freedom in the elements at nodes 1 and nodes 2. We will not be reviewing these kind of matrices within this presentation. It's beyond the scope of the work we're looking at, but this is an application of where matrices are often used. An overview. A matrix is a mathematical unit with elements arranged in rows and columns. If the elements are arranged in a different order, they produce different numbers. With matrices, various rules governing them have to be understood before they can be used to solve practical problems, and we'll obviously be looking at these rules in this presentation. A matrix does not have a single numerical value and cannot be simplified to a particular answer. The main advantage of using matrices is that by applying the laws of matrices, they can be simplified by manipulating one matrix with another matrix, and then values of unknown elements can be determined. You'll see this in applications, particularly in later presentations. Matrices can be added, subtracted, and multiplied, and most of the operations we use obey the laws that govern algebra of numbers. However, division of matrices is not possible. Determinants. Determinants arose due to the work of Kramer in connection with solution of simultaneous equations, often called Kramer's rule. Determinants are used within the manipulation of matrices when division is to be undertaken and we need to find the inverse of a matrix. Note there is a fundamental difference between matrices and determinants. A matrix is an array of elements, each having its own distinct position in the array. A determinant is a number obtained by combining the elements in the determinant in a prescribed manner, and you'll see in later presentations how we calculate determinants of matrices. Advantages of matrices over determinants. Once the inverse of a matrix is derived, This can be used many times over to solve various numerical problems with different vector arrays. This reduces the computational time and thus means, for example, many aircraft loading cases can be solved in a much shorter time than if determinants were to be used. For example, when analysing an aircraft wing structure, we may develop a stiffness matrix. Once we found the inverse of the stiffness matrix, we can use it many times over for different load cases applied to the wing structure. And it's not uncommon for there to be 1,000 or even 5,000 load cases applied. So once you have the inverse of a matrix, it becomes a very quick process to find the deflections for each of the load cases using computer software. We'll review the basic elements of this process in later presentations. An introduction. Consider the linear simultaneous equation shown on the right hand side. We have 5x minus 3y is equal to 7 and 4x plus 7y is equal to 15. These equations can be written in what's termed matrix notation. In the first matrix, I have the coefficients of the x and y. Here are the coefficients of the x values above. Here are the coefficients of the y above. In the second matrix here, I have the unknowns, x and y, and they are equal to, on the right hand side, the constants of 7 and 15. So essentially, a matrix is a rectangular array of numbers. The order of a matrix is always specified in terms of n by n. An n by n matrix contains n rows and n columns of numbers. Introduction continued. So in the diagram below, we have the first row and first column shown, and the first element there is denoted as A11. So A11, first row, first column. Next we have the element A12 denoting the first row, second column. Next A13 denoting the first row, third column, up to the A1n, the first row, nth column. In the next row we have element A21 denoting the second row, first column, then A22, second row, second column, A23, second row, third column, up to A2n, second row, nth column. And so the third row is denoted by element A31, A32, A33, up to A3, etc. So in this particular matrix we have m rows and n columns. For future reference, this diagonal is often termed the leading diagonal of the matrix. So the general element of a matrix, denoted up here in our sketch, is stated as Aij, where I is the ith row and j is the jth column. Matrices are generally denoted by capital letters such as matrix A, matrix B, K, P, or Z33, etc. The algebra of matrices. So 1. The addition of matrices is what's called associative. In other words, A plus, in brackets, B plus C, gives the same value as A plus B plus C. 2. Addition of matrices is commutative. In other words, A plus B is equal to B plus A. 3. Multiplication of matrices is associative. In other words, A multiplied by B and C in bracket is equal to AB multiplied by C. 4. Multiplication of matrices is not commutative. In other words, A multiplied by B does not equal B multiplied by A. So be very careful in later work where we start multiplying matrices together. Item 5. Multiplication of a matrix by a scalar value such as k, where k is a number. Then k multiplied by matrix Aij is the same as k multiplied by every element in the matrix Aij. Item 6. Division of matrices. We need to use the inverse property. If we are given the sum matrix A multiplied by matrix B is equal to matrix C, and we're asked to find the matrix B, then that is not matrix C divided by matrix A. That will be written instead as matrix A to the minus 1, in other words the inverse of matrix A, multiplied by C. Note also the location of the inverse matrix, the a to the minus 1, because matrices are not commutative, therefore the a to the minus 1 must be on the left hand side of the C when we do the calculation to find matrix B. Again, something we'll highlight in later presentations. Standard matrices. Some terminology for us here. Number 1. The row matrix. The row matrix, m by n, is said to occur when m is equal to 1. So this is a row matrix with elements of A, B, C and D. This is a 1 by 4 matrix. 2. A column matrix. A column matrix has the order m by n, where n is equal to 1. So this column matrix, A, B, C, D, is written as a 4 by 1 matrix. 3. The null or zero matrix. The null matrix contains all zero elements. So in matrix algebra, the null matrix behaves like multiplying by 0 in general arithmetic. So here is a 2 by 2 null matrix having 4 elements. Here is a 3 by 3 null matrix having 3 by 3 elements. Standard matrices continued. Item 4 is a square matrix. A square matrix has the order m is equal to n. Here's an example of two square matrices, the A, B, C, D, E, F, G, H, I, and the 5, 9, 33, 23, 2, 0, 19, 6, 12 are examples of 3 by 3 matrices. They're both square matrices. 5. Unit matrix. The unit matrix is a diagonal matrix of non-zero elements, all unity, all the value of 1. So for example, a 2 by 2 unit matrix is 1, 0, 0, 1, and a 3 by 3 unit matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. A unit matrix can be denoted by the symbol I for identity. So if matrix A is another square matrix of the same order as I, then matrix A multiplied by the matrix I is equal to the matrix I multiplied by matrix A, which is equal to matrix A. In other words, the value of matrix A is unchanged when it's multiplied by the identity matrix. Matrices and rules of arithmetic. Only matrices having the same order, 2 by 2, 3 by 3, can be added or subtracted. The laws of addition and subtraction can be applied to more than 2 matrices. So we could have 3 matrices that are added or subtracted. 2 by 2 matrices can be added together by adding their corresponding elements. However, a 3 by 2 matrix cannot be added to a 2 by 2 matrix, since some elements in one matrix do not have corresponding elements in the other matrix. The sum of 2 matrices is the matrix obtained by adding the elements occupying corresponding positions in the matrix, and this results in 2 matrices being simplified into a single matrix. Example 1. We're asked to consider addition and subtraction of matrices A, B and C given below. Matrix A is a 2 by 2 matrix, matrix B is a 2 by 2 matrix, matrix C is a 3 by 2 matrix, i.e. 3 rows and 2 columns. If we're asked to evaluate A plus B, then we simply add the corresponding elements in the 2 matrices. For example, matrix A, we have 2, first row, first column, and that's added to, in the matrix B, 3 in the first row, first column. For matrix A, in the first row, second column, we've got negative 1, and we add to that for matrix B, first row, second column, negative 5. Now matrix A, in the second row, first column, we have 1, matrix B, in the second row, first column, we have 2, so 1 add 2. Matrix A, second row, second column, we have 0. And matrix B, second row, second column, we have 1. So we simply add up these values to find the result of A plus B. So 2 plus 3 is 5, negative 1 minus 5 is negative 6, 1 plus 2 is 3, and 0 plus 1 is 1. If we're now asked to evaluate A minus B, it's essentially the same process involved, but this time we will be subtracting, not adding, the individual elements from the different matrices. Just be careful of double negatives that can occur with this kind of process. So evaluating matrix A minus B, we find the coefficients would be negative 1, 4, negative 1, negative 1 from the calculation shown. If we're now asked to evaluate matrix B minus A, same process, but this time the matrix B coefficients are placed first in this matrix, so these are matrix B coefficients here, and we subtract from that the matrix A coefficients, the 2, the negative 1, the 1, and the 0. Evaluating, we find we get elements 1, negative 4, 1, and 1. And finally, we're asked to evaluate matrix A plus matrix C. Matrix A is a 2 by 2 matrix, and matrix C is a 3 by 2 matrix. So we can clearly see we do not have the corresponding elements in matrix A to add to matrix C. So in this case, we cannot perform the arithmetic calculation because the matrices are not conformable. So to pick up from the previous slide, we must note that matrices can only be added or subtracted if they are of the same order. So A and B are second order 2 by 2 matrices, i.e. 2 rows and 2 columns. However, matrix C is an order 3 by 2, 3 rows, 2 columns. So note when adding matrices, it is true that A plus B is equal to B plus A, and note also that when subtracting matrices, it is true that A minus B is equal to negative in brackets B minus A. Tutorial questions on worksheet 1. Matrices A, B, C and D are given, shown here, they're all 2 by 2 matrices. We're asked to determine a single matrix for each of the expressions. So question 1, part A, we're asked to add matrix A to matrix B. Part B, add matrix A to matrix C. In question 2, part A, we're asked to add matrix C to D, and 2B, add matrix B to D. The answers are shown in the square brackets here. I would encourage you to stop the presentation and attempt problems 1 and 2 as shown here. Tutorial questions, worksheet 1 continued. Problem 3, part A, we've got matrix B minus matrix A. And in part B, we've got matrix D minus matrix B. And in question 4, we've got more subtraction problems. In question 5, we've got 3 matrices in part A to add, A, B and C. And in part B, we've got matrix A minus matrix B plus matrix C minus matrix D. All these matrices can be added or subtracted because they are all of the same order, that is, all 2 by 2s. We're now going to consider matrices and multiplication. Firstly, we're going to look at multiplication by a scalar value. So when a matrix is multiplied by a number, that's a scalar, the resultant matrix is of the same order and each of the elements is multiplied by the scalar or number. So when multiplying a matrix by a scalar, note that every element within the matrix must be factored by the scalar value. Example 2. We're asked to consider scalar multiplication of the following matrices. We give a matrix A a 2 by 2, matrix B a 2 by 2, matrix C is a 3 by 2, 3 rows, 2 columns. So firstly we're asked to evaluate 3 multiplied by matrix C. So 3 is a scalar, matrix C is given above our 3 by 2 matrix. So all we do now is multiply each of the elements in matrix C by 3. So in other words, the first element, first row, first column is negative 3, multiplied by 3 is negative 9. First row, second column element is 2, so 2 multiplied by 3 is 6. And so the process is repeated for the second row. 0 multiplied by 3 is 0, negative 1 multiplied by 3 is negative 3, and for the final row, negative 1 multiplied by 3 is negative 3, and 4 multiplied by 3 is 12. So we have our solution to 3C. Next we're asked to evaluate a half multiplied by matrix A minus 2 multiplied by matrix B. So given the above information, that becomes a half multiplied by matrix A minus 2 multiplied by matrix B. Applying the scaling factors to the individual matrices, a half multiplied by 2 gives us 1, half multiplied by negative 1, negative a half multiplied by 1, positive a half multiplied by 0 is 0. We're taken away from that, 2 multiplied by 3 is 6, 2 multiplied by negative 5 is negative 10, 2 multiplied by 2 is 4, and 2 multiplied by 1 is 2. So now we've completed the scalar multiplication. Now we simply have to subtract the respective elements in the two matrices. So first row, first column in our first matrix is 1, and we're taking away from that first row, first column in the second matrix, which is 6. So 1 take away 6. So first matrix, first row, second column, we've got negative a half, and we're subtracting from that, from the second matrix, first row, second column is negative 10. Be careful here of a double negative when we undertake our subtraction. Process is now repeated for the second row. So in our first matrix, the second row, first column is a half, and we subtract from that from our second matrix, second row, first column is 4. So subtract 4. In our first matrix, second row, second column, we've got 0, and from our second matrix, we've got second row, second column is 2. So we subtract 2. So evaluating the half A minus 2B, for our first row, first column, we get 1 minus 6 from above, so that's negative 5. For our first row, second column from above, we got negative a half minus a negative 10, so be careful of double negatives there, that's 9.5. For the second row, first column from above, we've got a half take away 4, so that's negative 3.5. And for the second row, second column, we've got 0 minus 2, so that's negative 2. Exercise 1 relates to scaling of matrices. Below is listed the average monthly mileage for a company's fleet of vehicles stated by region. We're asked to write this information in matrix format and using matrix manipulation determine a matrix that states the vehicle's mileage by region, but related to annual, not monthly travel. So in the table, we're given the average monthly mileage travelled by a company's vehicle, that's by region. So cars for the northwest, Midlands and southwest are given mileage here per month. Same for the vans, mileage given per month for the various regions, and same for trucks, mileage given per month. We're now asked to write this average monthly mileage information in matrix form and convert it to annual mileage. I suggest you stop the presentation and undertake this exercise. The answer is given here. A full work solution is shown on the following slide. So in exercise 1, we were given the list of average monthly mileage for the company's fleet of vehicles. That was stated by region. We're asked to write it in matrix form and then using matrix manipulation determine a matrix that states the mileage by region, but in terms of annual mileage, not monthly travel. So placing the information into matrix form for the monthly travel, for the cars per region, for the vans per region, and then for the trucks per region. So that's just writing the information in matrix form per month. As there are 12 months in a year, then the monthly mileage has to be scaled by the factor of 12. So my matrix for yearly travel will be 12 times the above matrix of monthly travel. So applying the factor of 12 to every element in the m months matrix, I end up with my m year matrix, and I'll let you work through the calculations at your own pace, as shown here. This is now a matrix for regional mileage per year. Matrices and multiplication. That is a matrix by matrix multiplication. Two matrices can only be multiplied together when the number of columns in the first matrix equals the number of rows in the second matrix. This is because the process of multiplication depends on finding the sum of the products of the elements in the rows of the first matrix with the elements in the columns of the second matrix, as illustrated below. So multiplying the first row of the first matrix by the first column of the second matrix allows us to calculate the first row, first element of the final matrix. So in other words, A multiplied by E plus B multiplied by G will give the value of the element in the multiplied matrix. It is possible to multiply a 2 by 2 matrix by a column matrix having two elements, or by another 2 by 2 matrix as shown above, but it is not possible to multiply a 2 by 2 matrix by a row matrix. The following slides will illustrate the process of multiplication using matrices and highlight the above conditions that must be complied with. Example 3. We're asked to consider multiplication of the following matrices. Matrix A is a 2 by 2, B is a 2 by 2, and matrix C is a 3 by 2. So we're asked to evaluate AB, that's matrix A multiplied by B. So matrix A is 2 minus 1, 1 and 0. Matrix B is 3 minus 5, 2, 1. So to multiply these two matrices together, we multiply the rows in matrix A by the columns in matrix B. So generically now, to find the first row, first column element in our final AB matrix, we have to multiply the first row in matrix A with the first column in matrix B. So that will be 2 multiplied by 3, shown here, and we then add to that negative 1 multiplied by 2, shown here. Be careful of our signs. That will be 2 times 3 is 6, and we add to that negative 1 times 2, so that's really take away 2. So that gives us a value of 4. Now looking at the first row, second column in our final solution for AB, what we're going to do now is multiply the first row by the second column. So now that will be 2 multiplied by the negative 5, shown here, and we add to that the negative 1 multiplied by the positive 1, shown here. Evaluating, that becomes negative 10 minus 1, which evaluates to negative 11 for our element in AB. Now we're going to evaluate the second row, first column element in AB. To do that, we will multiply the second row in matrix A by the first column in matrix B. So that will be 1 multiplied by 3, shown here, added to 0 multiplied by 2, shown here. Evaluating, that's 3 plus 0, or simply 3 for the second row, first element in AB. And finally, we want to find the second row, second column element in matrix AB, shown here. To do that, we multiply the second row in the matrix A by the second column in matrix B. So we have 1 multiplied by negative 5, shown here, and we add to that 0 multiplied by positive 1, shown here. Evaluating, that's negative 5 plus 0. That produces a value of negative 5 for element in row 2, column 2. Example 3 continue. We're now asked to evaluate BA, that's matrix B multiplied by A. So this time B is the first matrix shown here with the 4 elements. And we're multiplying that by matrix A shown here with its 4 elements. The process is now identical to that shown on the previous slide, just that we're multiplying rows in matrix B by columns in matrix A this time. I'll let you wander through the arithmetic. What you should find is that BA is equal to 1, -3, 5, -2. In other words, notice that the multiplication of matrix A by B does not equal to matrix B multiplied by matrix A. And finally, we're asked to evaluate AC, which is matrix A multiplied by matrix C. Matrix A is a 2 by 2 matrix, matrix C is a 3 by 2 matrix. What we notice if we try and multiply the first row in matrix A by the first column in matrix C is that there is an incompatibility. There are not the corresponding elements available to undertake the multiplication process. So this cannot be performed in this particular case, as the matrices are not compatible. As with matrix addition, matrix multiplication cannot always be undertaken as the matrices are incompatible. Example 3 continued. We're asked to evaluate CA, that's matrix C multiplied by A. Now here we'll find that we can multiply matrix C by matrix A because we have the same number of elements in a row in matrix C as we do in a column in matrix A. So we can now multiply a row by a column to give this solution here, follows through here and to here. Similarly, we can multiply the second row in matrix C by the second column in matrix A to produce this value here, which will follow through to this value here to here. Similarly, we can multiply the third row in matrix C by the second column in matrix A, and that will produce this calculation here, which follows through here and gives us a value of 1 in the final matrix CA. I'll let you start the presentation and think through the various row multiplied by column calculations that are undertaken to find matrix CA and all the elements that are shown in the matrix here on the right hand side. Don't forget, we are always multiplying a row in matrix C with a column in matrix A. Exercise 2. This involves adding, subtracting and multiplying matrices. Below is the cost per item in pounds of bolts, nuts and washers. The components are classified in terms of 2 diameters and 2 material types, that is carbon steel denoted CS and stainless steel denoted SS. In part A, we're asked to form 3 2 by 2 matrices relating to the separate costs of the bolts, the washers and the nuts. In part B, using matrix addition, we're asked to calculate the total cost of each bolt, washer and nut assembly. Part C, if the minimum order quantity for all types of diameters is 1200, we've got to determine using matrices the cost of each of the assemblies. And finally part D, if the stainless steel items are subject to an additional 7% handling cost, we've got to create an appropriate second order matrix that factors the cost of only the stainless steel assemblies by 7%. That is, it leaves the carbon steel items unchanged. So here's the information given. We've got 2 diameters, 12.7 millimeters and 25 millimeters. We've got our carbon steel bolt, 0.1, 0.15 cost. Stainless steel bolt, 0.2, 0.3 cost. And we've got diameters 12.7 millimeters and 25 millimeters for our carbon steel washer and our stainless steel washer, and finally for the diameter of 12.7 millimeters and 25 millimeters, we've got the carbon steel nut cost and the stainless steel nut cost. I'd encourage you to start the presentation here and attempt exercise 2, but a full work solution is shown on the following slide. Exercise 2, solution, part A. We're asked to form 3 2x2 matrices related to the information in the exercise, which is repeated above for convenience. So firstly, considering the bolts, the information given in the question for the costs is shown here for the various diameters and material types, and it's been written into matrix B here as a 2x2 matrix. If we now consider the washers, the information given in the exercise is shown here, again in terms of cost. I've written that into matrix W, the 2x2 matrix shown here. And finally, if we consider the nuts, the information for the nuts related to costs is shown here, again for the various diameters, various material types, and I've shown that in matrix N here, as again 2x2 matrix. So there's our 3 2x2 matrices for the bolts, the washers and the nuts. Exercise 2 continued. I've just repeated matrix B, N and W here for convenience. Part B, we're asked to calculate the total cost of the carbon steel assemblies and the stainless steel assemblies. I'm going to call that matrix C1. So C1 here will be the cost of a bolt, plus the cost of a washer, plus the cost of a nut. So this is matrix addition. So matrix C1, I've got the cost of the bolts shown in the first matrix, the washers shown in the second matrix, and the nuts in the third matrix. So add up the values of the assemblies for a 12.7mm bolt, nut and washer of carbon steel. I will add these three values here in my matrix to give this value here. To find the cost of a 12.7mm diameter bolt, nut and washer in stainless steel, I add the element here from the bolt cost to the element here for the washer cost to the element here for the nut cost, and that gives me the total cost of the stainless steel assembly here. Similar process applied to the 25mm diameter assemblies. I add this element here for the bolt to this element here to the washer, this element here to the nut. So that gives me this element here in my final matrix C1 for the cost of a 25mm assembly in carbon steel. And finally, to find the cost of a 25mm stainless steel assembly, I add the cost of the bolt to the cost of the washer to the cost of the nut to give me this element value here in my final matrix C1 for the cost of a 25mm assembly in stainless steel. Part C, we're told that the minimum order quantity is 1200 items of each type. So I'm going to call this matrix C1200. So this is a scalar problem matrices. So to find the C1200 as I've labelled the matrix, we simply factor all the elements in the C1 matrix by 1200. So that produces the four elements shown here in the C1200 matrix related to the cost of 1200 assemblies of the above bolts for diameters and material types. Exercise 2 continued. I just repeated the bolt matrix B, the nut matrix N and the washer matrix W from the previous slide. Don't forget these matrices relate to the cost of the various assembly items for the 12.7mm assembly in carbon steel and stainless steel and for the 25mm assembly in carbon steel and stainless steel. In part D, we're asked to include a 7% handling cost, but on the stainless steel items only. So we're going to determine matrix C1200H as I defined here. So matrix C1200H will equal to matrix C1200 from the previous slide. Don't forget that's the cost of 1200 items of the above types of assemblies multiplied by the matrix CH, which is the handling matrix. In matrix CH we have the elements of 1, 0, 0 and 1.07. The 1.07 relates to the 7% additional cost that will be applied to stainless steel items only. What we will do now is apply matrix multiplication, and you will see that the 7% additional handling costs will be added to the stainless steel items only in the C1200 matrix. So in matrix multiplication, we multiply a row by a column. So taking the first row in the C1200 matrix by the first column in the CH matrix, we get this sum to calculate. That's 228 multiplied by 1 plus the 434.4 multiplied by 0. Evaluating this gives us the first element in the C1200H matrix, which is 228. As we can see, this first element is unchanged from the C1200 matrix because there is no handling cost applied to carbon steel items. If we now multiply the first row in the C1200 matrix with the second column in the CH matrix, we find that we do get an increase of 7% on the stainless steel items. This will now produce this sum here for the C1200 matrix multiplied by the CH matrix for element in row 1, column 2. We notice now in the C1200H matrix we have a 7% increase in the value of the stainless steel items shown in the C1200 matrix above. If we repeat the procedure now for the second row in matrix C1200 with the first column in the matrix CH, we find we will get this calculation here, second row, first column, which evaluates to 324, and again we can see there's no change in this value from the C1200 matrix because that's a carbon steel item. And finally, if we multiply the second row in the C1200 matrix with the second column in the CH matrix, we find we get this calculation here, and again we will see that there's a 7% charge now added to the stainless steel items in the C1200 matrix above. So what we have here is a C1200 matrix now includes the 7% handling cost, but it's applied to the stainless steel items or stainless steel assemblies only.
Matrices and multiplication continued. So if we multiply a 2 by 3 matrix by a 3 by 2 matrix, we get the following generic outcome. So multiplying the first row by the first column produces this element. Multiplying the first row by the second column produces this element. Multiplying the second row by the first column produces this element, and multiplying the second row by the second column produces this element. So in other words, multiplying a 2 by 3 matrix by a 3 by 2 matrix produces a 2 by 2 matrix. Exercise 3. The results of 5 soccer clubs in the first 12 matches of a football season are stated in the 5 by 3 matrix shown. This is the 5 by 3 matrix. The points awarded for a win, a draw, or a lose are stated in the column matrix shown here. We're asked to calculate a matrix that contains the total number of points scored by each of the clubs. We're asked to state which club has the most points. This is a matrix multiplication problem and the answer is shown here. Exercise 4. We're asked to multiply the following matrices together. Part A. A European airline has an aircraft fleet consisting of 6 Airbus A321s, 4 A319s and 2 Boeing 777s. An American carrier has 3 Airbus A321s, 6 A319s and 1 Boeing 777. We're asked to write this information in terms of a 2 by 3 matrix. Part B. The Airbus A321s and A319s and the Boeing 777 accommodate 185, 124 and 305 passengers respectively. We've got to write this information in a 3 by 1 matrix. And finally, part C, we're asked to multiply these matrices together and state what quantity the matrix represents. The answer is shown here. I encourage you to stop the presentation here and undertake exercise 3 and 4, although full work solutions are shown on the following slides.
Exercise 3 solution. I just repeated the results matrix R and the points matrix P from the previous slides for convenience. We've got to now find the total number of points that each team achieved. so that means multiplying matrix R by P. So to find our P, we multiply the first row in matrix R with the column vector P. Calculation is shown here, and the number of points for Aston Villa is 16. Next, taking the second row in matrix R, multiplying that by the column matrix P, and these calculations here, and that gives 11 points for Bristol City. Considering the third row in matrix R with the column matrix P, find these calculations, and the total number of points for Bristol Rovers is 21. This is very good because it means we've got more than Bristol City. Continuing the process on, we find the points for Stoke and Wolverhampton. So what we find ultimately that Bristol Rovers has the largest number of points, which is pleasing to me because that's my favourite football team.
Exercise 4, solution. Part A, we were informed that the European airline has an aircraft fleet consisting of 6 Airbus A321 aircraft, 4 A319 aircraft and 2 Boeing 777 aircraft. An American carrier has 3 Airbus A321 aircraft, 6 A319 aircraft and 1 Boeing 777 aircraft. We're asked to present this information in a 2x3 matrix. So matrix A here related to the aircraft, we have the European airline with its 6 A321s, its 4 A319s and its 2 Boeing 777s. And the USA aircraft carrier has 3 A321s, 6 A319s and 1 Boeing 777. Part B of the question informs us that the Airbus A321, A319 and Boeing 777 accommodate 185, 124 and 305 passengers respectively. We've got to write this information in a 3x1 matrix. So for the passenger capacity of the aircraft, matrix P I've called this. For the A321, 185 passengers. For the A319, 124 passengers. And for the Boeing 777, 305 passengers. So now we've written the information from the question for parts A and B in terms of the appropriate matrices. On the next slide we'll look at part C of the exercise.
Exercise 4, solution continued. Now we've got to find the total number of passengers that each airline can accommodate. So we need to multiply matrix A by matrix P to find AP. So again we multiply a row by a column. So there's the calculations for the first row by the column matrix P. So 2,216 passengers can be carried by the European airline. Multiplying the second row in matrix A with matrix P, we find these calculations here, which gives us a value of 1,604.
I will leave you with some tutorial questions to attempt related to multiplication of matrices. You're given 5 matrices defined here, A, B, C, D and E, and in questions 6 through to 10 ask you to undertake various matrix multiplication exercises. The answers are shown in the square brackets on the right hand side of each question. I encourage you to stop the presentation and attempt these questions now. Here is the bibliography used to generate the presentation, some very good books related to engineering mathematics. I hope this has been of interest to you and thank you for viewing.